In our first video, we aimed to provide some intuition as to the general strategy that we'll be employing in order to find volumes of revolution with what is sometimes called the disk method. What I'd like to do now is be more precise in exactly what we'll be doing to find volume. Again, I'd like to go back to the precise version that we used when discovering our formula for area. When we were determining the general formula for finding the signed area between a curve and the positive x-axis, we used the following picture. We had our curve plotted here and our rectangles beneath the curve. The first thing we did is determine the length of any one of the bases of the rectangles underneath the curve. And that was given for us by the length of our interval, endpoint minus start point, divided by the number of rectangles. And because that value was constant and the same for each one of the rectangles, we called that dx, where the dx is standing for the small difference in x values. The height of each of our rectangles was provided by the function evaluated at one of the endpoints of the interval we were looking at. So if we were at the ith rectangle, the first, second, or third rectangle, we would use the height of the function evaluated at that point to tell us the height of the rectangle. All we needed in order to find the area of one of those rectangles was the length of the base and the height, and we would find the area of the rectangle by multiplying those two things together. And in general, our approximation for the area underneath that curve was found by summing all of the individual areas. Notice how very little changes when we switch from area to volume. My picture has changed some because what I did with my original picture was rotated it around the x-axis. So this circle here in red is indicating that rotation. And what we'll want to envision in our head is that each one of these rectangles has also been rotated around the x-axis. And in doing so, we've made a cylinder. What was formerly the length of the base of any one of those rectangles is now representing the height of that cylinder. And it's the same value, dx. What was formerly the height of the rectangle has now become the radius of that cylinder and is given by the value f of x sub I. Just like we had a formula for the area of a rectangle, we have a simple geometric formula for the volume of a cylinder, and that's given by pi times the radius squared multiplied by the height of the cylinder. Here, our radius is f of x sub I, so the radius squared part of that cylinder formula is f of x sub I quantity squared. The dx value is actually the height of our cylinder, and so this is pi times the radius squared times the height. This expression right here is giving the volume of one of the individual cylinders, and so just as we did with area, we'll find the total volume by adding up each of the individual volumes of the cylinders. When we then aim to make our approximation as good as we could possibly get it by taking the limit of this entire expression down below as n approaches infinity, all that will happen is this sum will change to an integral sign, and instead of summing from 1 to n based on the number of rectangles, that integral sign will have bounds from the start of the interval to the end of the interval. And that will be our generalized formula using the disk method for finding a volume of revolution in this way. To complete the example that we started with, that is, considering the curve y is equal to the square root of x from 0 to 4, that region being rotated around the x-axis, that picture would look something like this, where our whole curve has been rotated around the x-axis, and each of our little individual rectangles has been rotated around the x-axis to form a cylinder. In order to solve this problem, we walk through step by step thinking about what would happen if we took one of these basic rectangles and rotated it around that x-axis. The height of one of these tiny cylinders would be given by dx. The radius of the cylinder, the distance from my axis of rotation out to here, is given by the height of the function. In this example, our function is the square root of x. Using our basic volume formula for the volume of a cylinder, we have pi times our radius squared times our height, or in other words, when we take the square root of x and then we square it, we're going to get just x. So altogether, the total volume of revolution is obtained by adding from 0 to 4 the volumes of each of the individual cylinders. It gives us a very nice, easy integral to compute, and when we use the fundamental theorem of calculus here, the answer we obtain for the volume of revolution for this shape is given by 8 pi.